So if we evaluate this one, the actual equation was isn't it 4 minus 3x, something like that?
Yeah.
So it's 4 minus 3x. I'll change that to t though. Keep our dummy variable correct. So let's see what happens. Ultimately, if we anti-differentiate here, we're going to get 4t minus 3t squared over 2. Negative 1 to x plus k, keep in mind. And then on this side, same deal, 4 minus 3t squared over 2. 3 to x. Right? So if we plug in an x here, let's see what happens. If we plug in x, we're going to get 4x minus 3x squared over 2 minus, and if we put a negative 1 into that, we're going to get negative 4 minus 3 halves. Square root of the negative 1, we'll get 1 plus k. And then over here, we got 4x minus 3x squared over 2, of course, minus, and if we put a 3 in there this time, we're going to get 12 minus, and putting a 3 in here, we get 9 times 3, 27 halves. Now, again, keep in mind we're going to find k here. What's going to happen if we, when we start putting stuff together, we have this quantity here and this quantity here on the either side of the equation. If we start subtracting, those are going to be gone, aren't they? Just convenient. That'll leave us with just k then, won't it? The variable. So bottom line is inside the parentheses here we have negative 5.5 essentially. So be negative, if we make this 2 to be 8, so it'll be negative 11 halves. So it'll be positive 11 halves plus k. The opposite of subtracting that quantity. And then on this side we have, this would be 24 halves minus 27 halves. So it'd be negative 3 halves. And it's minus out here, so positive 3 halves over here. And if we subtract, we get k over here. 3 minus 11 would be negative 8 halves. So ultimately, this would be negative 4 like we showed. Alright. And what was the other question?
Find d dx, so negative 1 to x of f of t.
Negative 1 to x of same f of t.
Yep.
So ultimately, this part has no bearing on the previous part because we're just finding the derivative of an integral function here. And so we know by the fundamental theorem, first part, that if we have a derivative of an integral function, that the answer is the integrand, evaluated at the upper limit, times the derivative of the upper limit. So isn't the answer just simply 4 minus 3x? So again, most common mistake on a fundamental theorem problem like that is people try to anti-differentiate the f. Okay. Is it an anti-differentiation problem here? No. It's a differentiation problem. You're differentiating, you're not anti-differentiating. Okay. So ultimately the derivative of an integral defined function, again, is the integrand evaluated at the upper limit. Don't do anything with the integrand besides put the upper limit in there. Don't differentiate it. Don't anti-differentiate it. Okay? It's just the integrand evaluated at the upper limit. And then if the upper limit has a derivative other than 1, then you got to multiply by the derivative of it. But in this case, since it's just x, derivative is 1, so it doesn't change anything. What else? Anything else on the practice test? And 10, you got particle moving along the coordinate axis, and so we ultimately know that our f function shown here is the area function defined by s here, and ultimately keeping in mind that if the position is s, then we're in this graph that we have is f, that this is really essentially a velocity graph here. Okay. So we're ultimately again looking at a derivative. So keep in mind we're looking at the derivative of our function. And in part A here, it says what is the particle's position at time 0? Well, keep in mind again the integral here is defined as the s integral, which is our position, is defined as from 0 to x of f of t dt. Well, keep in mind again, if we put for part A, if we put a 0 in there, what are we going to get for our area? 0. So that would be our initial position, if you will, our position at time 0. Okay. And then then part B here says what is our position at 3. So ultimately it's an issue of how much area have we accumulated by the time we get from 0 to 3. And what shape do we have there ultimately? As we go from 0 to 3, that's a line segment there. So wouldn't that shape be a trapezoid? So its area then, we just go 1/2 times the height there, of course, is 3. And then the 2 parallel vertical segments here, they look like they have, they don't actually give us a function here, do they? Well, we can figure it out because, you know, one thing you got to be careful with here is that we could just look at that and say, oh, it looks like 2.5 there for that one height. Obviously the other height's 1, we can see that, but are we sure that's 2.5?
No.
I mean, if you take that for granted and you're right, then great, but what if you're wrong? What if it was, you know, 5/11ths or something? Then you're going to be wrong then, aren't you? So how would we tell if it's right or not? Well, they give us 2 points on that, don't they? So couldn't we figure out the equation for that line and see what the y-intercept is? Okay. And you definitely need to do that. I'm telling you right now on AP problems, if it looks like it's 1/2, okay, probably not. Okay. It might be on this one, but not always. So ultimately the slope there we can calculate would be 1 minus 2. So we have the point 3, 1 and 1, 2. So 1 minus 2 and then 3 minus 1. And ultimately -1 over 2. So -1/2 would be the slope. And if we plug in our point here, we can use either point. But if we do y minus 2, -1/2, x minus 1. And we do the math, we got -1/2 x plus 1/2. And if we add, we get -1/2 x plus 2.5. So it did turn out to be 2.5 in this case, but again, don't take that for granted. Okay? If you have points, find the equation and make sure that's actually 2.5 and not just because it looks like it. So with that said, our 2.5 or 5/2 here, we get 7/4 would be 21/4. We got 2/2, so 7/2 times 1/2 would be 7/4, times 3 would be 21/4.
How are you finding this area? Because it's a trapezoid?
Yeah. And that shape right there, that goes from 0, 0 to 3, 1. If you draw a line down from 3, 1 down to the x-axis, that would be a trapezoid, wouldn't it?
And what's the area for a trapezoid?
1/2 times height times base 1 plus base 2. Alright, how about the next part here? What's the particle's velocity at time 5? Again, aren't we looking at a picture of the velocity? So what's the value of the function at 5? It's just -2, so there's no calculating to be done on that one. And how about part D? Approximately when is the acceleration equal to 0? Time what? It would be time 5, wouldn't it? It's like it's a minimum there. And ultimately the derivative of this is the acceleration. We're looking at a picture of the velocity. And then finally part E says at what time during the first 7 seconds does S have its largest value? Again, keep in mind we're starting at a value of 0. We calculated that in part A, right? And what are we doing from there? We're accumulating immediately positive area.
Yeah.
True. And we accumulate positive area up to a little bit more than 21/4 because we have a little triangle there, triangle type shape. We get a little more than 21/4, and then what happens after that?
Negative area.
Yeah, we're going to accumulate a bunch of negative area, and it looks like probably almost as much. We might be back down to 0 by the time we get over there to 7. True? So ultimately, where is the area the larger? Where have we accumulated the most positive area, if you will? Should be at time, it's like about 3.5. So ultimately, we're just estimating there again because we don't. That's not necessarily a line segment, so we can't really find the equation for that part. So we don't really know what that x-intercept is, but we can estimate to be about 3.5. They don't give us means to find that equation, so. All right, questions on that one? Anything else on the practice test? And 8, graphing the function. I'm assuming you're good on that one, right? Okay. So integrate. If we're going to integrate that, so just for time's sake here. And again, we're integrating from 0 to 6, and as you can see, from 0 over to 6, there are both negative and positive parts. Okay, as we go from 0 to 6. So keeping in mind, if we integrate that, we're going to get an answer that's going to be, looks like it's probably negative because it looks like there's more negative area than positive. Okay. But then what's the difference in that question in part B and part C when we want to find the area between the graph and the x-axis? Okay. What do we need to do with this part? We need to find it separate, and then we need to find this separate, and we need to treat this as positive and add them together. We're looking for a total area here. And ultimately, remember again, we can also do our integral command. If we do our absolute value, we can get the answer that way as well. Again, we can do this using the fundamental theorem also, depending on whether it's just something we can integrate or not. In this case, we could integrate it again, but for time's sake, we'll just do it for the calculator for time being. I'm assuming there wasn't an issue with the antiderivative or anything, right? Right. And we're going 0 to 6. 0.8. And looks like it should be about 7 1/3. About 7 1/3 if you did it by hand, I would imagine. Remember, the calculator doesn't know the answer. It's using an algorithm to estimate the answer. It's usually a pretty good estimation, but what else? Anything else on the practice test? Victor?
Number 11.
11, got a trapezoid rule problem. Says just use using 4 subintervals. Keeping in mind that the integral is from 0 to 2. So if we do 4 subintervals, then the subinterval length would be a half each. True? So that means that our h would be a half. That's the length of the subinterval. So it'll be a half over 2 outside. It'll be a quarter, of course. And then from there, we need to find our y values. We're starting at 0. If we do 0 squared minus 0, that's 0. And then if we put a half in there, we're going to get a quarter minus a half. True? Putting a half into that function, we get a quarter minus a half, would be negative 1/2. And then if we put a 1 in there next, we get 1 minus 1, which is back to 0. Then if we put a 3 halves in there, for that third subinterval, 3 halves would be 9/4 minus 3 halves. And keep in mind that 3 halves would be 6/4. So 9/4 minus 6/4 would be 3/4. And then finally at 2, we'd be at 4 minus 2, which is 2. And so ultimately it's just a matter of calculating that, and we're good to go. Okay.
I was just saying, for like the first one, for when you put in a half, isn't it negative 4?
Yeah, what did I say it was? It was a half in there.
It was a quarter
Yeah,
minus
you're
half.
right, quarter, not a half. Sorry, thanks. So the quarter in there instead of half, and then you're good to go. So ultimately just do the math on that, and it should give you the correct answer that we saw up there. Right. I don't know. Anybody write it down? How much? 38,400. And you notice on that number 12, all we're interested in here is just the area. This is not a volume problem. There's no depth to this lake or whatever. It's just a meadow, so there's no third dimension to it. So all we're doing is just doing our surface area, if you will. So ultimately, it's really no different than the problem we just did. Just know the spacing is 30, so that means we did 30 over 2 out in front.
The Simpsons rule.
Okay.
So.
We use Simpson's rule too, so we'd use 76, and then 4 times 118, 2 times 130, 4 times 143, and so on. All the way down till we get to 122, which would be times 4, and then a 60 on the end. Others? Practice test?
What time we got this class?
12.